All right, folks. We're going to start again. We have two orals, and we're going to start with Thomas Kipp, who's going to talk about dorsal diffusion for object-centric representations of scenes et al.
Hi, everyone. I'm pretty excited to be able to speak here today, especially since I just very recently moved to the Bay Area, and I'm very excited about the BayLearn Symposium. So my talk is about dorsal diffusion for object-centric representations of scenes et al., which stands for and others, so other things like scenes. And I'm presenting on behalf of our team at Google Research and spanning across both Google Research and Google DeepMind. And to summarize like what dorsal is about in a nutshell, dorsal is essentially a generative model that combines, on the one hand, object representations, and on the other hand, 3D into like 3D aspects into a single model. And so by object representations, we really mean to have something like a representation that represents something like a scene or like an image or a video in a representation where you have something like one token per object. So usually tokenized representations, you know them from language, where you might have like a token per word or for a word subunit. And so we're really focusing here on a representation where you can represent scenes in this kind of tokenized fashion. And on the other hand, we care about 3D. And that really in this context means we want to build generative models that have multi-view consistency and are able to render novel views. So those are kind of the 3D aspects. So something like what you can see here in this video, that you can basically kind of render a fly-through through a scene. And so why should we care about object representations in the first place? And so if you look at the world around you, like everyday scenes, like traffic scenes, or if you look at like images of animals, groups of animals, or even kind of like physical phenomena, the way we kind of reason about them and perceive them, what really kind of pops out to us is like the structure in terms of objects, like the cars or the animals, or like in this Newton's cradle example here, you can very well imagine like what happens next if like this ball swings into the other balls. And so objects are really core to human perception. And in the context of machine learning, they facilitate things like interpretability, compositional generalization, and data efficiency. So things we kind of have in language, but if you care about like understanding the visual world, it's sometimes really difficult to get these aspects into models. And so compositional generalization especially means like if you want to model a physical system and you want to generalize to kind of new versions that maybe look a little bit different, then object representations really support that kind of generalization. And for generative tools in particular, like creative tools and so forth, it's one important aspect, it's a very natural interface. So if you think about animation software, rendering software, or kind of video game development software, like thinking about assets and objects and how you place them in scenes is a very kind of natural way of thinking about this problem. And so why should we care about 3D? Well, our world is effectively 3D. And in addition to that, in machine learning, there has been massively exciting progress in 3D generation in the last couple of years. And especially nerves have been kind of taking the internet by storm. And you've all seen these kinds of videos where you can kind of create this nice like camera fly-throughs through scenes. And nerves, just in a nutshell, basically effectively optimize a single machine learning model for a single scene, kind of trying to overfit on a single scene, at least in the original paper, and kind of use volumetric rendering to facilitate this optimization problem. And so if you've seen all these videos, you might wonder, okay, why isn't this everywhere yet? What's kind of missing from like 3D? Back when we started looking into this problem in 2021, some of the limitations were effectively that speed is often an issue with these kinds of models. Like if you optimize a single model on a single scene, well, you have to go through the entire optimization process, and that can be expensive. Also, nerves, when you train them on a single scene, they typically have trouble generalizing. Like they can't really imagine what happens if you remove a certain object from the scene and what's behind that kind of revealed aspect. And so with generalization comes also sometimes this problem that you may need many views of a scene to really get these nice fly-throughs. So you cannot really, at least in the single scene optimization case, effectively do that from just a single image. And finally, if you want to do scene editing, like place assets or move them around or edit them, that also requires generalization in some form or another. And so the question we asked basically, and many others in the community asked, is like, how can we tap into the benefits of scale for 3D learning, similar to like how for language learning, scale and scalable architectures and scalable data sets really made all the difference. And so one architecture class we started looking into is the scene representation transformer. And it's effectively, as the name says, it's a transformer-based model for novel view synthesis. So what the model does, it doesn't have any kind of 3D volumetric rendering like NeRF, but it basically just takes views of a scene, like photos of a scene, and encodes them using a transformer into what the paper calls a set latent scene representation. So you can think of like just a set of tokens, and decodes it again using a transformer into pixels. And so conditioned on maybe like the viewpoint or the query race or the camera pose that you want to render this viewpoint from. And so what this allows you to do is to kind of train a single model across a wide range of scenes and render novel viewpoints and have like generalization to some degree. And now comes again like the object part into it. Like if we care about like compositional representations and being able to edit scenes in some meaningful way, one aspect we try to kind of put this into this class of models is by taking this architecture. Again, this is very similar to the scene representation transformer architecture you've seen in the last slide. You start with a set of input views, you encode them with a transformer encoder into the set latent scene representation, and then you apply a module that decomposes that representation into meaningful chunks. And these meaningful chunks, in the case of like visual scenes, are often things like objects or like macroscopic things you can kind of move around or move independently. And so slot attention here is the module that facilitates this kind of grouping. And slot attention is effectively a simple kind of attention-based module that looks a little bit like regular cross attention, like you would have in many transformer architectures. But as a small trick, it performs this kind of grouping operation. It's updated iteratively. So you run this attention mechanism iteratively, and at every time step of the iteration, it might group like a clustering algorithm. It might group the representation that you apply it to into separate composable units, like objects in this case. And finally, we decode those representations back into the image space using a per slot decoder. So we call the object tokens, we often call them slots, and they now represent like all the visual attributes of a particular object, and we can render those scenes then using a per slot decoder. So every kind of slot is now, you can think of it, so there are variants of this decoder, but you can think of it as like every slot gets decoded into the image with a clear attribution where it belongs to. And so we can visualize, for example, this attribution and get these nice segmentation masks that are 3D consistent. But now in terms of results, like what this facilitates is you get decomposition and novel view synthesis on novel scenes and novel objects in very fast speed, with one big disadvantage. Because these models are, as you can very clearly see, these renderings are very blurry. And these models are deterministic, and so if you have any kind of uncertainty around like what's behind an object or what's occluded, this gets resolved with kind of blurriness. And meanwhile, there has been massive progress in diffusion models, and they can kind of address this problem of like, you have uncertainty or like multiple options of how something can look like, for example, a text to image mapping, and via denoising diffusion, you can kind of resolve that uncertainty and create kind of crisp realizations of that. And so now back to Dorsal, what Dorsal now does is basically combine these benefits like with diffusion models, but use object-centric representations of scenes with the goal to be able to get high fidelity 3D consistent rendering and object level content control. And so the model we choose is effectively a video diffusion model. So it's like a video version of the diffusion model, condition on those object slots and condition on camera pose. So the object slots we get from this OSRT encoder, like you've seen in the past few slides, like this is this transformer encoder we can train on a big data set. We get these slots from it, the tokens that we can either get unsupervised, or we can also use segmentation information to facilitate that grouping. And finally, we condition a diffusion model not on language tokens like it is frequently done, but we condition on those object scene tokens, or these object slots and poses. And what this allows us to do is basically get a video diffusion model where we can kind of control the camera. So we get like few consistent camera path rendering. And by using some tricks in the kind of denoising process, and at least on these kind of scenes where we have like synthetic scenes with many different objects and realistic textures, you can create crisp kind of fly-throughs at arguably fairly low resolution in this case. We also trained this on Street View, and because the Street View cars, they only take images every so many kind of seconds or maybe 2 frames per second, not entirely sure, but like you can only interpolate between the frame rate basically, so we don't get like perfectly smooth transitions. And finally, what this representation supports, because it's decomposed into objects, is we can delete individual objects from the representation by dropping individual object slots. So you can kind of cycle through all the slots, and then in the bottom you see like objects disappear in a scene. But also in these kind of real-world Street View scenes, you can just edit a latent representation, and with a bit of luck, you find a slot that kind of results in deleting an object from the scene. Now this is far from perfect, but it's kind of an interesting use case. And what excites us most, I think, is like the fact that you can transfer tokens from one scene to another scene. Like you can encode one scene into these object slots, get the representations of the object out of it, and transfer that asset into another scene. And that gets rendered, like in the bottom right case, this car, it gets rendered correctly with the right lighting conditions and so forth. Again, this is a fairly low resolution, but it's a nice proof of concept. So in terms of conclusions, Dorsal is a model that combines objects, 3D, and diffusion. It's interesting to see that they can repurpose video diffusion models for novel view synthesis and 3D rendering. And by conditioning on object slots and text instead of text prompts, we get direct control over individual objects in the scene. There are many limitations still and next steps. So as you can see, all of these results are pretty low resolution. There are, of course, ways to address this. There are things like cascading diffusion models or latent diffusion models that allow you to do much higher resolution decoding. The object edits are far from perfect. Like the control is somewhat finicky at the moment. And multi-view consistency is still a challenge. You can see, if you look very closely at these videos, they're very low res, but you can still see like the legs of these tables are sometimes flickering and other parts are sometimes not perfectly consistent. With that, thank you for your attention. I think we have a short moment for questions. Otherwise, you can also find us at the poster later. Thank you.
All right.
Hi, my name is Jiading Fang. I also work on 3D reconstruction. My question is, I just look at poster. I look at your result and your GT result, right? The thing is, yes, they're crisper than previous works. However, they are not view reconstruction, meaning that there are new objects there. It's not the actual result, the actual object that you want to reconstruct. It's kind of view imagination. So how do you comment on that? Is this really what we want? Second question, I remember the original SRT takes about $1 million. I calculated it to train. What's the training cost here? Is it even more? And then also that it's actually low resolution. So what's the use case that you imagine for this line of work to be effective? Or I guess according to the scaling, are you expecting that it works like LLM, that once it gets to even higher scale, then it will somehow become actually useful? Yeah.
Those are really great questions. To your first question, I think you can see like the card slightly changes appearance. I think these are just aspects of like how much is captured in the representation about the car and how well also the diffusion model can actually fit that data. And these are things that over time will improve by basically just training more higher quality models. But indeed, this is a limitation at the moment. In terms of training costs, like it's hard to point out specifics. Like people have reproduced in academia like results from SRT. And also people have trained like these kind of smaller scale video diffusion models. And I think this is kind of what this model here combines. So basically, Combining these two architectures, especially at this low resolution stage, it's not like it doesn't require massive amounts of compute to train. But of course, like as you train on bigger and bigger data sets, this becomes a kind of concern.
All right. Oh, wait. One more question? Okay. One last one.
Hi. So slot attention, had originally I had seen applications of it in some robotics, for robotics applications. So does this have also robotics applications, or is it just for graphics, 3D graphics and things like that?
That's a great question. So the robotics application, that was really on the representation learning part. Here, the focus is really just the kind of rendering aspect. So that's yet another kind of application of it, I would say. But these are more or less orthogonal.
All right. Let's thank Thomas. All right. We have one more presentation. Is it you also? Oh, yeah. Okay. Oh, you're going to have to plug in? Okay.
All right.
Okay, great. Hello, everyone. I'm Dhruv, and I'll be talking about this paper called WINT, a foundation model for visual navigation. Throughout the day, I think a lot of speakers have alluded to why robotics is a hard problem, and I'm a little disappointed there's not other people talking about robotics here. So hopefully I'll try to represent the community a little bit, and then at the end we can all agree it's a really hard problem. Great, this is work jointly done with Ajay and Nitish, who are also here in the audience and will be at the posters. So I guess this is a machine learning venue. We don't need to convince anyone that robotics is great. And there's been a lot of robot learning results in the last couple of years. This is just slides of videos that I pulled up from the last 2 to 3 years of papers where people have shown that for a variety of tasks, manipulation, for drones, for navigation, all sorts of things, machine learning works great. But if you really look under the hood and what these systems are doing, there's generally 2 classes of methods. So the first one I'll talk about is the RT1 and RT2 line of work from Google, where it's super cool that it can do all of these open vocabulary, manipulating objects and interacting with the real world. But under the hood, the policies that were trained to make this happen were done with hundreds of robots and thousands of hours of data collection, which there's been papers about it, but really a lot of people spend a lot of time getting these systems really working. So they trained with real world, so a lot of the policies that learned were really, really good. But then it required on-robot data collection, which is very, very expensive, and it does not scale to other robots. And at the same time, it's really hard to generalize to new tables, new tabletops, new robots, and so on. The other line of work is kind of like the bottom. We have this super fast drone that's from Zurich. It's spinning it through forests. And to get that to work, we use this thing which is called simulation to real transfer, where we simulate an environment that is kind of similar to what the real world would look like. In this case, it's they render depth in simulated forests, which is at least easier to scale. But then you really need to model every environment that you care about in simulation, which is not great if you want open world robots. And at the same time, this only really works if you're trying to transfer depth. RGB images don't really generalize that well. So why is robot learning in the real world so hard? Well, as a starter, the real world is really hard to simulate. If you could simulate every aspect of the dynamics and perception in a simulator, you could solve robotics. But that's not something we can do unless we actually live in a simulation already. Right. And the cost of collecting data itself is super hard. I would not have the numbers, but you could guess how much those hundreds of KUKA arms collecting data for the Google robot cost. And it may be outright infeasible for a lot of systems. So here, there's this very small drone that folks at MIT developed, which has a battery life of about 5 minutes. If you really need thousands of hours of data collection, wouldn't be feasible. And this is true both on the perception side as well as on the dynamic side. So I propose that we don't need to look too far for a solution. I won't get too much into the technical aspects of the talk, but conveniently, our poster is right here, and we can continue the discussion right after. So before we go into robotics, let's take a brief primer of how AI used to work back in the day. And when I say AI, I use it fairly broadly. So we would have a lot of data. We would have a segmentation model that takes an image, passes it through the model, and gets segments and labels for different parts of the image. You would have a classification model, a VQA model, a captioning model, all sorts of things. And this used to work really, really well. Chris referred to this as dying with 1,000 cuts. This used to work really, really well. But then, as we all know now, what we do now is we take this large amount of data, which is weakly supervised or unlabeled, weakly labeled, and then we train a giant unsupervised learning model, which in this workshop we'll call it a foundation model. And people would take this, take a small amount of data that they care about, and fine-tune the model or prompt the model in a zero-shot way so that you would get a segmentation model that you care about or a classification model that you care about. And of course, this seems to work really well for NLP and vision, as we found so far. So what I propose is, what would such a recipe look like for robot learning? So right now, you have these different models for different kinds of embodiments that different people have in their labs. You have a small amount of robots. You have some data that you collect on your own robots. And then they do some interesting tasks like indoor navigation or quadruped locomotion or off-road driving. But perhaps in the future, we can go towards a vision where you take all of these data sets, robot or non-robot data sets, you collect them, and you define some sort of a weak metric, such that a weak labels, so that you can actually use all of this data. And then you train this giant unsupervised pre-trained model, which we will now call a robot foundation model. And then you would fine-tune it with a small amount of data that's taken from a robot in your own lab, and then it would solve your task well. And hopefully and in the process, this will also give you the same benefits that it's given the other communities, like a very efficient adaptation. And before we go any further, I want to touch upon the choice of the phrase robot foundation model. I'm just going to define it for the sake of this talk, and then we can debate about whether it's a good definition or not. So to define it, we would say it's a model that you train once using whatever amount of data, whatever amount of compute that you care about. And it can be deployed zero-shot in completely different and useful settings. So this would be different sensors, different robots, different environments. And in addition to that, you can adapt it to a downstream task of choice. So this would mean different objectives from what it was trained with, a different goal specification, or a different behavior. And what I'll describe now is one such effort that we have for the task of navigation, show what it does, and then we'll check back if this definition was a good one. So broadly speaking, there's 3 sets of challenges towards this goal: developing algorithms for training these models, collecting and assembling the right sort of data sets so that these models actually learn useful behaviors, and of course, designing kind of a flexible and general purpose model that can absorb all the data set and can be trained in a somewhat scalable way. So in the future, when we have more data, we can train even better models. And just to be clear, the aim is not to get a model that is really good at maxing out all of the benchmarks that may or may not exist, but really to kind of have a pre-trained backbone that can do a lot of interesting tasks, and then you can hand it to someone, they can fine-tune it, and it does useful things. All right, so for the algorithm, we will talk about how do we define some sort of a self-supervised objective that makes sense. The thing that we've found works really well for a lot of robotic tasks is just using goal condition BC. No other supervised algorithms right now. We just use 2 labels given a set of data sets. Given a video, you take 2 frames of the video, and a self-supervised objective is predicting the number of frames between them. That's what we would call a temporal distance. And given a trajectory or a robot video, you already have the action labels, which you assume were collected in the data set. So these are the only 2 labels, and you train the model using goal condition behavior cloning. For the data, it's really hard to obtain, robot data. So we reached out to a lot of universities who are collecting data sets, and we asked them to share their data sets with us. We converted them to a format that works, and we have this data set of around 10 navigation robots, in different environments, different tasks, different embodiments, the robots ranging from super small and super big, and they kind of form a convex hull of embodiments that we think represent good navigation robots. And lastly, for the model, unsurprisingly, transformers work really well. So this is fairly similar to the RT1 style transformer that Google used, where observations and goals are encoded as tokens. And then you have a large self-attention block that looks over all the observations in your past, conditions it on the goal, and predicts the labels that we talked about. So the model that we have, which we call the Visual Navigation Transformer, or VINT, takes these observations, which is a small temporal context of past observations, and the goal processes them using a convolutional backbone. So you have some tokens corresponding to observations and goals, and then you pass it through a transformer block to predict your actions, which in this case would be both distances and actions. And what this kind of architecture lets you do is, as long as you have data with the right set of labels, you can train this model on all the data that you have available, and it enables a lot of zero-shot as well as few-shot adaptation kind of frameworks. So without getting into how we trained it at all, I'll just throw it out there that we trained it, and it actually does work. So not only does it solve the tasks for each of the robots that we care about, but it also generalizes zero-shot to new robots, to new sensor placements, to new environments, and it can be adapted in a very nice way. So very quickly, something that breaks a lot of robot policies, if this was a more robotics audience, you would resonate with this. If you move the camera slightly, everything breaks. Because when you collected your data, the camera was fixed in a certain pose. So we just showed that if you have this model that is trained with a camera placed on 3 different heights, and you give it a goal that is to find a certain stuffed toy in a corner of the building, they all kind of succeed and they all reach there. Well, it's not super cool that just moving the camera helps. What this really means is now you can take a completely new robot, and it's a new camera and a new body, and all the model sees is it sees the small feed that's coming in at the bottom left, and the model needs to decide, well, where do I go so I don't collide into my obstacles while I'm still reaching the goal. And then this is a drone. There were no drones in the training data, but the model just generalizes to drones. Similarly, there were no quadrupeds in the training data, and we just applied the model on a quadruped, and the quadruped also learns these interesting behaviors, like how do I avoid collisions with walls, and I keep exploring my environments. And similarly, we did this on indoor robots, on outdoor robots, all sorts of things. So we have a model that actually works for a lot of different tasks, and it generalizes fairly well across all of them. And if you wanted to fine-tune it, you could fine-tune it. But the nice thing about using an architecture like the transformer, which everyone has been using, is we get a lot of these, even though the scale of this model, what 50 million parameters, is really, really small compared to what we see in language. We see a lot of these nice emergent properties, like, for example, prompt tuning, already happening at the scale that we have. So if you take a robot a model that you already had, conditioned on goal images, and let's say now you don't have goal images, but you have language or text or positions for your goals that you want to make this model work with. So what you could do is you could remove the goal token, fine-tune a new head, which goes from your desired goal modality to your token space, and leave the rest of the model where it's pre-trained. Then you now have a model that can condition on commands like turn left, turn right, or GPS positions. And rather than training a whole model again for these new modalities, you can just efficiently fine-tune this model with a very small amount of data for the tasks you care about. There's a lot of kind of things I wanted to touch on, but very quickly, I started off with this definition at the start, which is it should be able to deploy zero-shot in different environments, and it can be adapted to a lot of different objectives. Well, we can do a lot of objectives in terms of this prompt tuning and just fine-tuning the model, but the part that's super, super exciting to me is, I'll skip all of this because I'm out of time, but that we released this code of these models. So this current paper came out a few months ago, but the previous version was about a year. And in the last year, on GitHub, we have a lot of people who have downloaded these models, deployed it on their own robots in different labs, different countries entirely, with I dare say, minimum effort on my side because I'm lazy. And it actually does work. So it's not just that it's me and my collaborators who can make this work. Here's an example of the model that we trained in Berkeley being deployed in Finland or in Estonia or in Princeton. And it's doing the task. It has a completely new robot that I have not seen before. The model was fully pre-trained a year ago, and it was put on these robots, and these robots are moving, not hitting anyone, and kind of solving some task. Chris mentioned briefly that something that would be very exciting is if we can scale up the models and data and work on just converting robotics into a sequence modeling problem. Here's a project that was a follow-up of the WIN project where we just went all in and collaborated with, I think, 100 research collaborators and just took all of their data, trained a very large model on it, and deployed it in 10 different university labs, and it actually still works. This is not navigation anymore. This is pick and place, language condition, all sorts of tasks. And it's really promising to see that just taking inspiration from the language community and applying some of these techniques to robotics, we have a lot of cool problems that we can solve. And that's my time. I can take questions now and also at my poster.
All right, any questions?
So in your talk, everything seems to be working great. So what is not working?
That's a great question. So I think the right answer for this is we are nowhere close to maximizing the capabilities of any of these robots. So the task that I set off for myself at the start is, let's say you want a model that works on 10 different robots. The best thing you can hope to learn is some sort of an average behavior that is conservative and safe for all of them. But if I really wanted a robot, a model that would max out the capabilities of a drone that is zipping through a forest, I don't know how to do that right now, other than collecting more data of those really high tasks. So none of this is the maxing out the capabilities or performance of any of these systems. It's kind of just focusing on the generalization aspect. And hopefully the thing that we would do eventually is we would collect a small amount of data which is really good at the task we want to solve, and either fine-tune this model or figure out a better model that can do it.
So in your architecture, you have shown convolution network and then the transformer, right? So have you tried end-to-end transformers, like 16 by 16 patches that way?
We have, yes. So we tried the more VIT style of doing it, where you just convert everything into patches and process that. My recollection is that it works, but the simpler thing works better. The very nice thing about using something like convolutions is we just have a lot of pre-trained efficient net or ResNet backbones already available, so we can bootstrap the training a lot more. But certainly, I think going fully end-to-end attention also, if I remember correctly, did somewhat work, but worse.
And if you can describe the learning objective here, your data is images, but what's your label output? Is the next image in the frame or what?
Yeah, so the input to the model is the current observations and the goal image, and the output is the temporal distance, which is number of frames between them if this was a video, and the action itself. So if you have a robot trajectory which has images and actions, then the actions are the label, as well as if you have the current image and the goal image, how far they are. So you're predicting distance and actions.
Okay, thank you.
Hi, thank you. So how long before, you can use YouTube data, humans performing in the, doing things in the world and motion capture and things like that before you can use it in addition to the data that you have for different types of robots and transfer that? And yeah.
Yeah, that's a great question. I think just as a community, there's been a lot of work on doing, the third-person imitation, which is from humans to robots. But also, if you really think about a human with a head-mounted GoPro versus a robot that's going, on a sidewalk, the data is not that different. And I think at least at the level of perceptual features, it is very easy to get that transfer working. I think we have some early work where we already see that helps. But on a more philosophical level, I think it's hard to determine what kind of things we want to transfer. If you're thinking about behaviors, then a human walking in a crowd will face different interaction with other humans around it versus a robot in a crowd. Like you might want to, stay away from the humans. Other humans would behave differently if it was a robot versus if it was a human. So there's, at some point, we'll have to figure out what we actually want to transfer from, these third-person and passive sources to real robot sources. But at least at the level of visual features, it's definitely very easy. Oh, for manipulation? Yeah, I think there's plenty of work that at least does some version of it, but I don't think there's been a big consolidation of like just YouTube to robot directly.
But a good project for next year. All right, let's thank Drew.